I am going to be discussing the 9.2 section, our angle addition identities for trig. There are three types of problems that I'll be asking you to do based on this section. I'll be asking you to simplify expressions using our addition identities and evaluate exact values for non-reference angles using our identities, and then we're going to do a few more proofs using these angle addition identities. So what are the angle addition identities, or what are we talking about? We're looking at things like the sine of x plus y. So we're adding two angles and wanting to find the sine of the sum of those. So to start with, I want to look at what the identity could possibly be. So a lot of times people want to think that the sine of x plus y is the same as sine of x plus sine of y. So let's take a look at that idea by just picking two values, one value for x, one value for y, and we're going to plug it in on each side and see if this comes out to be the same, because if this is an identity, it should be true everywhere where both of the values are defined. So that will look like this. So I'm taking pi over 4, plugging it in for x. I'm taking pi over 3 and plugging in for y on this side. And then I did the same thing on the right side. On our handy-dandy calculators, so just to take a look at just this piece, I'm going to use the calculators to kind of take a look at what's happening. So if I plug that in on my calculator, and I take the sine of pi divided by 4 plus pi divided by 3, I get the value 0.9659. And on the right side, if I do sine of pi divided by 4 plus sine of pi divided by 3, we get 1.57. Therefore, these two things are not equal. And since they weren't equal for that x and y value, that means the original equation is not true. So beware, don't try to call sine of x plus y sine of x plus sine of y. Instead, what we're going to use is the sine of x plus y is equal to sine x cosine y plus cosine x sine y. Where did that come from? Well, deriving this is actually pretty complicated, and I know I often still show you that stuff, even though you don't often, breaking my heart, don't want to see it. However, this one is so complicated that I am not going to go into it. It is available online. It does still involve triangles on the unit circle. However, it's a little bit more complicated. However, what we're going to do is just kind of take a double check, same thing we just did above, just to see that it does work. I know you're probably saying, Mrs. Peterson, we believe you. However, just to verify, because sometimes you shouldn't believe me, we should all know, if we again make x pi over 4 and y pi over 3, in this equation it would look like this. So we found on the calculator that this was 0.9659. So I'm going to plug this side in on the calculator to see if it comes out as the same thing. I'm going to clear that out there. Sine of pi over 4 times cosine of pi over 3 plus cosine of pi over 4 times sine of pi over 3, and we do get the same thing mathematically. Again, it's not something that intuitively looks like it should make sense, but these do end up being the same thing. This is not a proof, what we're doing, because it only is showing that it's true for those two values. Just for funsies, just to plug in one more set of values, just to see that it works. Again, still wouldn't be a proof because we're still only showing one more set of values. So I'm plugging 1 and 4.2 in. I should say y is 4.2. So the sine of 1 plus 4.2 can be rewritten as the sine of 1 times the cosine of 4.2 plus cosine of 1 times sine of 4.2. Sine of 1 plus 4.2, enter, negative 0.883. Sine of 1 times cosine of 4.2 plus cosine of 1 times sine of 4.2. And it's the same thing. Again, it's not a proof that these two things are equal. However, it's just a verification that it's pretty sure it works. And again, if you want to see the proof, it is out there on the interweb. And it is an interesting proof. So this is just one of our identities from 9-2, our angle addition identity. We also get the cosine addition identity, and we also get the sine and cosine subtraction identities. So all in all four of those identities look like this. Oop. I quit halfway through on this one. So sine of x plus y is sine x cosine y plus cosine x sine y. Sine of x minus y, sine x cosine y minus cosine x sine y. And then cosine x of x plus y is cosine x cosine y. And crazier yet, minus sine x sine y. And cosine of x minus y is cosine x cosine y plus sine x sine y. All together, because of the switching of the sines and the cosines where they are, the x's and the y's where they are, what's added, what's subtracted, these can be a little bit confusing to keep track of. I will provide you with these identities on any test or quiz or skill check. You just have to be able to use them. So these four identities that we'll be using, I will provide them to you, and you just have to use them. Okay? So I'm going to now look at two types of examples. The other example I'm going to save is going to be a proof, and I'll put that on another video. So our first example is we are going to simplify cosine of x minus pi over 2. So to do this, we have to use one of our identities. So this is the cosine of x minus something. So I'm going to use the cosine subtraction identity. And just with replacing the y with pi over 2. So using the cosine of subtraction identity, this is the same as cosine x cosine pi over 2 plus sine x sine pi over 2. Pi over 2 is an exact value. I can find sine and cosine of that, either thinking on the graph or thinking of our unit circle. Pi over 2 is on the positive side of the y-axis. The coordinate there is 0, 1. Cosine of pi over 2 is the same as the x-coordinate in that spot, so that's 0 plus sine of x times the sine of pi over 2 in that spot is 1. This is 0. This is just sine x, so we end up just being at sine x. Which is really, when you think about it, just makes sense also, because this is just a phase shift right of pi over 2 of cosine. So therefore, that would leave you with sine. The next example that we're going to do is actually finding the sine and cosine of angles that are not our reference angles. So for example, we're going to look at the sine of 17 pi over 12. So we're going to use our angle addition and subtraction identities. You have to find a way to take 17 pi over 12 and rewrite it as either the sum of two reference angles or the addition or the subtraction of two reference angles. You can do either one. You end up in the same spot. The angles that you want to add, you want when you rewrite it, them to reduce to one of our reference angles. So you want it to reduce so that we have something over 4, something over 3, something over 6, or something over 2. So the two angles that you either add or subtract, you want to reduce down to one of those sets of denominators. So I don't want to use 1 and 16. 1 pi over 12 is not one of my reference angles. However, if I use 2 pi over 12 and 15 pi over 12, 2 twelfths reduced down to pi over 6, that's a special guy, plus 15 over 12 reduces down to 5 pi over 4. That's another special guy. So once I can rewrite the initial angle as the sum of two of my special angles by thinking through that and reducing, and it might take a little bit of trial and error. And again, there's more than one way to do it. But then I can rewrite back here that this is the same as the sine of pi over 6 plus 5 pi over 4. I then can apply my angle addition identity for sine. Sine of x times cosine of y plus cosine x times sine y. So I'm just going to replace my x with pi over 6 in this case, and my y with 5 pi over 4. So I'm going to provide you with those identities on the skill check and on the quest. However, while you're doing your homework, you might want to rewrite them at the top of the page just so you can reuse them. So again, it's the sine of pi over 6 times the cosine of 5 pi over 4 plus cosine of pi over 6 times sine of 5 pi over 4. Pi over 6, however you think through it, your reference angles, if you're in a unit circular, it was a reference angle, pi over 6, that's a 30-degree angle, and you're in the first quadrant. So I'm looking at a 30, 60, 90. This is root 3, 1, 2. And 5 pi over 4 is a 45-degree angle, and that's going to be in the third quadrant. So I have my 45, 45, 90, 1, 1, root 2. So then I can go back through and fill in my exact values. Sine of pi over 6 is the same thing as the sine of 30. So that's 1/2 times cosine of 5 pi over 4. And I actually forgot to put my negatives in there. That's kind of important, or really a lot important. So cosine of 5 pi over 4 is negative 1 over root 2. or just negative root 2 over 2. And then plus cosine of pi over 6 is cosine of pi over 3, so plus root 3 over 2 times 5 pi over 4 negative root 2 over 2. So I get negative root 2 multiplying these over 4 plus negative root 6 over 4, negative root 2 over 4 plus root 6 over 4 becomes negative 2 minus root 6 all over 4. And you can't see the end there, sorry about that. So therefore, the key to these problems is really you have to know finding the sine and cosine of your special reference angles. And you have to be able to take whatever angle they give you and rewrite it as, again, the sum or the subtraction of any, or the sum or the difference of any two of your reference angles. And again, it might take a little bit of playing with, but they start to look pretty similar. This should get you through the first chunk of the 9-2 homework that is posted.